let's start with our binary trees, right? So idea, of course, is we have data is not often presented in a simple chain or an array or sort of sequence, right? We have data which might be linking to more than one item, right? And in this case, we'll start with looking at the simplest case of the tree, which links to two items, basically, right? So again, basic terminology, right? You may have seen somewhere, I don't know if how much of tree structures you covered already. Probably not too much, right? Not too much. Some, right? So there will be some, maybe a slight overlap, right? So the traversal, again, look at how to traverse, because we've been doing it already a little bit, right? But also how to actually implement this in C++, right? So on how to traverse different approaches how to traverse, right? So definition is simple. You either have a empty, right, a tree, or it has nodes, right? You have a root node, and of course there's a left side and right side, basically a subtree, right? And of course those could have a subtrees as well, right? So something like this, right? And eventually, of course, how do you present it? Of course, this could be a null pointer, most likely, right? Usually it's done because I'll use some other sentinel value, but usually something like this. So you have 1, 2, 3, 4, how many? Let's see, how many nodes? That's 4, 5, 8 here, right? But yeah, so where do we use them, these? Right? We use them, of course, for, well, provide some properties. Left side has some property, let's say less than the right side, of course, usually. But there are other ways of doing it, of course, right? So, one node, two nodes, three nodes, well, two nodes, right? Right, left side, right side, and of course, with three nodes, and so on, right? And again, it's possible that, of course, there are different ways of showing it. Like we have other ways of showing three nodes, right? Like this, or maybe like this, or this way, or this way. Right? So, four different ways of doing it. But of course, if compared here, right, this has also three nodes, right? So, again, different possibilities. And again, of course, this could be a different, this could represent what? A path. Maybe some sort of path you're going through somewhere, right, of possibilities. Think of like a tree could represent a question game. Yes, no, yes, no. You answer a bunch of questions. So it represents a traversal in some sort of search space. That's just one of many possibilities what a tree could represent. So, for binary trees, by default, of course, it has at most two children. So node has to have some reference to the data. It could be an integer, could be a, I don't know, string, could be some object, right? Storing some information, you know, about itself, some properties, attributes, and also, of course, it has to keep track of where the left and right side is, you know, which are, of course, pointers to themselves, to a node type, right? That's how we're going to implement it, right? So, of course, we'll need also a root pointer to the root, right? Because that's where we know where we start, right? So let's see how we implement this. And again, we have some terminology. So leaf, right? So what's a leaf? Leaf is something where it ends, right? Meaning it has no children. Leaves are like the endpoints, basically, right? So a parent, right? Of course, there's a branch, or we can call it an edge, right? So there is trees have this possibility. So one who knows one key property about trees compared to graphs? Trees are a type of graph.
They are sorted.
Well, not necessarily. We will have some sorted ones, but I mean we can sort them, right? But some other property, right? You have nodes and edges, right? But tree is lacking what? Tree guarantees something.
Well, there are no loops.
No loops, exactly. Very good. So there are no loops, right? So there is, and also it by then means there's unique path from root to every node, right? There's only one way. If there's no loops, right, there's no way of taking alternate route, right? Because then you have a loop, right? If there are two ways of getting somewhere, you know, you could imagine if this undirected graph, right, you could go back different way, but there's no. So it's unique paths that kind of goes together, right? No loops or unique paths, same thing basically. I mean, leads to the same conclusion. So length is basically how many branches, how many hops, I call them hops, how many hops you have to take. So level is if root is usually in level 0, sometimes some literature call it 1, but we'll call it 0 for now, right? So height is from root the longest path to some leaf, right? So this is how high. How high is this one here? 4. Let's see. I'm thinking 1, 2, 3. Is there 4? 1, 2, 3, right? Yeah, if you're not counting, I'm not counting to the. So height will be 3, right? Assuming if you have only root, you have height 0, right? Again, off by n errors, right? You have to check. Sometimes there's different ways of counting, but I would say this is height 3, right? 1, 2, 3, right? Because you're not counting these ones because it leads to nothing, right? To leaves. Because we count to the depth of the leaf. This is a leaf. So how many leaves do we have here? How many leaves?
8.
How?
8.
Well, no, leaves with no children. Meaning the endpoints, right? 3. 1, G, E, H. 3. Yeah, because this also counts as leaf, right? So again, this is not a leaf because it still has one child, at least one child, right? So, all right. So now we have some, again, this terminology will come up again and again, right? So it's pretty common, right? Just you have to be careful of some of these tiny off by 1 errors, right? So let's make it. Let's make a 3. I think that might be. You can see this in practice. Do we have a GitHub? Let's see. Shouldn't be too hard, right? So same approach we use with linked list, right? We are going to create some sort of structure, like a node, probably something like that. I guess I'll start with an integer-based one. Of course, making universal template-based one would be a better approach. But for now, I think at the beginning I'll start with the integer one. So let's do a binary tree. Binary tree. Let's make it. All right, but where's my binary tree? Here we go. Okay. Let's make a binary tree structure. We will use node struct that holds integers. All right, so let's start with that. Include IOStream. Include, well, yeah, vector. Do we want vector? Yeah, I guess I don't know what do we want vector for. I suppose. Include Q. I wonder why it's adding some things which I mean stack, okay, yeah, but for now, I'm not gonna, well, we'll see, I won't see what's gonna happen. Algorithm, okay, math, I think it's getting too ambitious. Yeah, it's getting too ambitious, right? So yeah, that's basic, so that's our basic building block, so, our basic building block, right? Do we want to have a constructor here? I guess we could, right? Constructor. Yeah, there we go. That will work, right? So that would be a constructor, right? Null pointer, right? A basic constructor, right? Okay. Okay, that we have. So this part here again. So pointer. So pointers to left and right children of same type, right? Just like we use in linked list, right? Okay, and now we just define our tree, right? And we will define some methods, right? So let's make our tree structure. Again, I'm using, or you could make it class. Well, I guess, well, I suppose class would be better. Node is completely public, right? I have the data is completely public. Let's make a class. Let's make a binary tree class. Okay, thank you. Yeah, that's what I want, right? So public is node root, and we have a initializer, right? So what do we need? We need what? A function to insert a node. So how do we insert something? First of all, if we have no root, the easiest way is if we have root, right? Then we have nothing. We just make a root. The new node is the root, and that's it, right? Insert a value, right? But now this gets really, really crazy. yeah, insertion will be kind of, we'll maybe get to this part here. Maybe we'll see what the slides say about insertion, right? So it's dynamic data structure, right? So that's why I suppose, right, we have to keep adding, you know, allocating memory and deallocating memory, right, for these because we have a, you know, we keep inserting elements, right? That otherwise kind of really not very useful structure, right? So so let's look at traversal. So we need insertion also, right? So and we have many different ways of traversal: pre-order, in order, post order, for example, right? Which are the main ones. But let's see about creation, right? Well, first of all, how do we insert things, right? Well, if you just have it's a binary tree, does not mean, well, if you have no rules, right? You just want to insert somewhere, right? If you just random insert, basically, right? Find the next open space, right? Let's do this, maybe, right? Right. Insert node in next empty, next available position. When I say next is defined as by level or traversal. So we'll be traveling on these levels, right? Okay, so we start here, right? So we make a new node, right? This is the easy base case is very easy. Now we have a queue, right? Let's see. We push root, right? So we push root inside. We have queue, okay? Because basically we remember what property queues have. For queue, what property? What's property of queue?
First in, first out.
Yes, bless you. So first go in. So that's, you know, so it has a priority. You know, so first, so we push the root in, right? Now, while we still have something in a queue, we check the front, basically, right? We pop, right? We have temporary, right? And we pop, if left is null pointer, we solve the problem, right? Otherwise, right, we push it back, right? Means we have one more node, one more level to go, right? How about right side? Again, and we are done, right? Again, we push again means we have one more level to go, right? Now, so we push, right? Temp left, temp right, right? We check both, basically, right? So either, so think about it, right? So this looks pretty decent, right? So while we have something to do, right, we will be exploring it, right? So how about deletion, right? That will be quite difficult. Well, again, if root is null pointer, we have nothing to delete, right? But now, again, we have a queue, we go a root, right? We have a key node, right, null pointer, and temporary node, and while we have something in a queue, we get it out, right? First element of the queue, you know, the first in line, right? We need a reference, we pop it, right? Remember why we have to do this two ways, because this does not return anything, right? In C++, pop does not return the value. In Python, typically pop returns something, right? In C++, front, right? For our queue, right? We will return the value, and we check, right, whether this matches, right? So first 10 tenths matches, right? We remove it, but then there's the issue, right? If it matches, key node is temporary, right? We need to push it, otherwise it's not null pointer, right? This will be very tricky on delete node. Do we have delete deepest? What is this part here, right? Deepest node, right? So again, we have a queue, we push root, well, it's not empty, we pop, and we now have to delete the root, the element. Okay, and this is not finished yet. Yeah. Let's take a look. parentheses we have here. Okay, alright, so one more parenthesis. Yeah, I guess we need one more. Okay, look at all these. So function is okay. Do we need one more? Yeah, semicolon. Okay, I think we are okay now. So we have insertion. Just basically, this is not a search tree. There's no order at the moment, right? For now, we are just putting some stuff. Of course, then we'll want to show this tree, right? That will be tricky, right? But let's see now. We also want to print this, right? Right, on the little on traversal. Right, in level order, right? So this would be what? Level order traversal would be what? What kind of traversal is it? If you go by levels, what does it smell like to me? Level order. Doesn't it smell like breadth first traversal, right? We keep going, right? It's empty. Same as is also called breadth. Yeah, that's BFS. Right. All right. So again, if nothing, we push the root. So in a way, there shouldn't be anything. We don't need any recursion here, right? So that will be for now. Should be relatively. I guess should be relatively clean code. Maybe what I can do is, of course, could we do the levels? It'd be nice to print the levels. Kind of hard, probably. Let's add a. This looks okay, but I would like to temp data, right? I guess we won't see the next level. I guess it'd be nice to see the level indicators, of course, too, right? What level you are, right? But we don't really have a good way of counting that, I guess. For now, I guess we'll leave it for now like this. Okay, so this is a breadth first traversal. All right, and now let's do this, right? So let's int main for now insert 1 2 3 4 5 6 7, right? Level order traversal, delete node 3. All right, let's see what happens. All right, looks okay to me. All right. So 1 2 3 4 5 6 7, right? All right. Let's compile it. I'm not 100% sure it's going to compile on the first try, but it might. Let's add all errors. Bin 3. Wow, it compiled. All right, yeah. So, interestingly enough, look at this part here. When we got rid of 3, the 7. So, let's see how this deepest depth. Everything works okay, right? Delete deepest, right? So we had to find the last one, right? Deepest node. And how did we move it, right? We delete the node, right? Because we had to move it, right? So basically, what we do is this, yeah. So we delete the deepest, right? And we move here in this particular instance, right? Here, right? We move the deepest node to the key node position, basically, right? So, temp, right? We find the deepest node, right? Undelete it, and then move the data, right? Key node, right? We sort of replace it basically, right? So it's not the only way to do it, by the way, right? So again, this is arbitrary. So we have this arbitrary structure basically, right? But we don't have any rules how we insert the data inside them. Bless you, right? So But at least we have this traversal, right? So breadth first of traversal. All right. Now I guess I will leave this, so this works. I will leave this off for now, but hopefully now we'll move on to other ways of traversal. So there's three more, right? So there's breadth first, and then there's depth first, right? But there's three variations of that first, right? So in order, pre-order, in order, post-order, right? So what does it mean? Basically, its basic question is, when do you do something called a visitation? Right? You have three structure, right? I guess I'll do my drawing here, right? I'm sure I'm gonna do my drawing here. Paint, right? I'll just do a tree. So we have our root, right? And we'll have some trees. Right. Something like this, right? So right, so left, right. Oops, oh, I can't spell. So left, right, and so on and so on, right? That's what we are talking about. Right, and then these are null pointers, of course, null pointers, right? Null, right? So I'm not even gonna draw this, right? Control Z, right? Null pointer, null pointer, null pointer, and of course now I'm gonna type the numbers. So I'll call it 1, right? 2, maybe a little bit bigger, but okay. 3, where's 3? 4, 5, 6, 7, right? Okay, so what we did is we did a depth first traversal, right? Or also, I'm sorry, breadth first traversal, right? Here we had a queue. So what we did is we check here. Okay, start here, right? You have any children? We add them to the queue, right? And we print this out. Then we print out 2, 3, 4, 5, 6, 7, right? So this is BFS, right? So let's do other traversals. Right, let's see if the book, if the slides say, right, so we want traversal, right, let's do in order, right, post order or pre-order traversal. So we visit the node and then we go left and right. So typically, how are these implemented, how are these traversals implemented to make it easy? How are they implemented? Using recursion, right? Again, for demonstration purposes, right, they are very easy to implement, right? So pre-order, exactly. Depth first traversal specific case is depth first traversal. One case of DFS of it, right? So pre-order traversal. Let's look at this code here before the break. We'll do a break in about a couple minutes. So if there's nothing, we return. So we need a base case scenario. We need a base case scenario, right? Otherwise, of course, we'll go forever, right? We have nothing to report, right? So we print ourselves first, right? And then we go left, and then we go right. So what will it print, right? So this is the question, right? So BT pre-order traversal, BT root. We need to provide where we start, I guess. This one takes a root, actually, by the way. We could start with the root, by the way. Well, the thing is, why do we need this? Because it's recursive. We make two recursive calls. We make two recursive calls then. Right. So this is pre-order. So let's see out pre-order, right? Did first. Right. So who can tell me in a pre-order traversal, who can guess what the numbers will look like? So let's think about this. So obviously in this case we are visiting, or visiting meaning doing something with a node. In this case we're just printing it out, right? So one, right? We're going to do one first, right? So what number will be printed next? What do we think? Look at the code here, right? Pre-order traversal. So we're gonna make a recursive call to the left, right? Which means a recursive call, you'll have this node. Yes, and of course, so it should print 2, right? 2, but then, right, it will also, it prints 2 and goes left again, so it print 4, right? And then we start unwinding the stack. Then we have 5, right, I believe, right? And then we'll go again, unwind stack 3, 6, 7, right? So 1, 2, 4, 5, 3, 6, 7. Let's see if my, so again, so depth first is, BFS 1, 2, 3, 4, 5, 6, 7, right? All right. Pre-order DFS will be 1, 2, 4, 5, 3, 6, 7, right? I think so, but let's double check, right? This is my hypothesis. Maybe I'm wrong, but if I should be correct. This actually was my job, one of the jobs I got like maybe over 10 years ago. I had to do this, right? A job interview actually, right? So, but I managed, right? But I was lucky because I had actually taken a class before, like maybe a couple months before, right? So, so it was relatively stressful, but I had to do it in C, not C++. Had no AI assistance. So it was pretty. So let's do this. Let's do this. And this is also famously, yeah. So, well, I didn't print it. So 1, 2, 4, 5, 3, 6, 7. Indeed. 1, 2, 4, 5, 3, 6, 7. Okay, I got it right still. All right. But yeah, you say, okay, maybe they did this 10 years ago, but still, Google still does this type of stuff again. And there was a famous case of the guy who works on a Mac brew, right? You know who has Macs here?
Roosters and Alberts.
Oh yes, they're not here, so they miss out on this, right? So, all right, maybe they have some sort of Mac convention or something. I don't know. Right, all right. Yeah, all right. Yeah, but so actually, and he didn't get a job at Google because he has a very famous tool and everything, but he had to do something with binary trees, and he failed basically. He had to reverse the binary tree, which is actually, well, it's kind of tricky, but it's not that hard once you do this, couple classes and you can do it, no problem. So, okay, so we did pre-order. Let's leave the other 2 traversals after the break. So let's continue at 12:10. I'll commit this.